dx2 is x1 plus I x2 and z2, this is z1, and x3 plus I x4. I apologize for the notation here, but anyway, it's just a standard Kähler, a standard flat Kähler form on our C2, and that's the standard. Every symplectic form locally looks like that, and we have the symplectic linear group, which is just a group of transformations which preserves a symplectic form, and sitting inside there is the unitary group, which is a maximal complex subgroup. And so what that means is that if you have a symplectic manifold and you look at its tangent bundle, well, you can reduce the structural group of the tangent bundle from the symplectic group, because they've written old local transformations line here, but you can reduce it to this because this is homotopy equivalent to that, to the maximum. So that means that this has almost complex structures. There exists a J, which is an operator for the tangent bundle to itself, where square is -1. And that minus the identity. So that turns the tangent bundle into a complex vector bundle. And this is called an almost complex structure. So you have this almost complex structure. And it turns out, if M is two-dimensional, dimension of M is 2, then J is integrable. And so that means that, in other words, there is a complex structure on the manifold itself, which gives you this structure on the tangent bundle. In higher dimensions, that's not. There's a condition, a stability condition due to Neuenhuis-Wolff. So in general, an almost complex structure in a four-dimensional manifold is not the same as a complex structure. It's not integrable. But for 2 dimensions, it is integrable. So what that means is that if you have in a manifold, if you've got this is 2-dimensional submanifold, say, and you ask that the tangent bundle to sigma is invariant under J. So you've put some almost complex structure on your manifold, and you ask the tangent bundles invariant under J. Then this 2-dimensional submanifold inherits a complex structure. You can think of it as a complex, as a complex curve, and that's a complex curve sitting inside your submanifold. So you can see some elements of complex structure coming out from just looking at submanifolds, which whose tangent, which are J. These are called J holomorphic curves, and they're actually there's a form of the Cauchy-Riemann equation. It basically they're parameterized. So J holomorphic curve. In general, you've got some Riemann surface mapping to some almost complex manifold, and you ask that du preserves J. So if you do your little j and then du, that's the same as doing it in the other order. So it's compatible. And this equation is like the Cauchy-Riemann equation. If you look at it analytically, it's an elliptic equation. It has finite. It's got Fredholm properties. It's got finite dimensional solution spaces. It's nicely behaved. So. And that's the theory of J holomorphic curves. Is this theory of the solutions of this kind of equation. So you could, and there's this one special thing. If you just look at this equation and do what I've said, there's no nice compactness properties for the solutions. That you have solution spaces, but they could degenerate. On the other hand, what Gromov realized is that you shouldn't just look at a completely arbitrary J here. You should look at what's called a tame J. If you look at the space of almost complex structures which you can look at so J is said to be tame if omega of VJV is always positive for any non-zero vector. That's a taming condition. That's a positivity condition. And so what it tells you is that then if you have a tame J, then you can get a metric. You can define G of V W to be omega of VJW plus omega of WJV, half of that. And that's a Riemannian metric. So this is, and so that means that you have a metric on your manifold, and that gives you compactness properties. That means that if you look at spaces of J holomorphic curves, then they can, they're not compact, but they have nice compactifications. So if J is the space of J holomorphic curves, in some, you fix a cohomology in some homology class, A in the manifold has an understandable compactification. And so what, for example, suppose you're in CP2 and you look at, the class A you're looking at is twice the line class. So you're looking at conics. And so there you look at the space of all of all these conics in CP2. That's not compact because they can degenerate into pairs of lines, right? You can degenerate into a pair of lines like that, or they could be two coincident lines. So you have this non-compact space. On the other hand, they can't do anything worse than that. That's what they do, right? You can explain that. And so in general, one of Gromov's, this paper he wrote, he introduced the notion of J holomorphic curves, and then he showed that for one thing, because this is a Fredholm operator, if you choose J as you've got a whole family, there's a infinite dimensional space of these tame J. So this is an infinite dimensional contractible space. So you have a huge amount of freedom. It's very, very different from complex geometry. You fixed your integrable J and that's it. Here you've got this huge infinite dimensional space of possible choices. But if you fix one, then you can choose a generic one. Then if you choose a generic one, you may be lucky and your space of J holomorphic curves is actually a manifold. The space of solutions is a manifold, but it won't be compact. But you can understand the compactification. It consists of unions of smaller dimensional curves. Now, of course, if you're in higher genus, if you're in genus 0, the only thing, the space of spheres, there's only one complex structure on the 2-sphere. And so the domain of your J holomorphic curve equation, this space here, for a sphere is very simple. It's just a point. And so the only thing that can happen with spheres is that something like happened here, that if you look in the target, you have some curve, and then a lot of energy starts, curve energy starts concentrating, and it forms like that, and a bubble forms, and so in the end it sort of looks like your curve, but you have a bubble attached to it. You've got a sphere bubbled off, and that's basically the only thing that can happen. If you're in higher genus, then of course the curve itself can degenerate, so that if you have a torus, it could generate into a union of 2 spheres. I mean, it could look something like this. Torus could degenerate into something like that, or it could have other, there are many more possible degenerations if you have higher genus. But in the case of a sphere, if your domain is a sphere, you have particularly easy things. The only things that can happen is this bubbling off. And so that's what's happening when you have a quadric and it degenerates too large. Anyway, so there's a good theory here of J holomorphic curves. And then what he did was use that to try and understand the structure of symplectic manifolds. And one of the things he proved was, so suppose we take S2 times S2, and we suppose we're omega, it's a 2-form, a closed 2-form. So suppose it lies in the class A1, well, so let's suppose that the integral of omega on the first sphere is equal to the integral of omega on the second sphere. So you've got 2 spheres of equal size. That's your cohomology class. And then he also assumed that you have assume that it exists a symplectic embedding of S2 wedge S2. So you've got one two sphere sitting inside like that, and you've got another two sphere sitting inside there, and they're symplectically embedded. And then, you know, if you're looking at a symplectic form on a surface, that's just an area form. And basically all area forms, if you fix the area, they're all diffeomorphic. So there's no invariance there. You could just assume these are completely standard S2 sitting and parameterized just in the obvious way, like Z goes to Z naught, Z or something. It just obviously. So these are standard spheres, and then you assume that the form you have here restricts on there to the usual area form and restricts on there to the usual area form. And then there's there aren't too many local symplectic invariants because of Darboux theorem here, that all symplectic forms are locally local. Well, extensions of that tell you that the symplectic form, there'll be some little neighborhood in which the symplectic form looks completely standard, like the product of two things. But then you don't know what's happening here. And what the theory of J holomorphic curves is, you choose a J for which this is holomorphic and that is holomorphic, which you can always do. And you know, there's a lot of choice of this J. You can extend it. If you've got it fixed somewhere, you can extend it, make it compatible. And then he shows that you can extend this family. You're going to have a family of spheres here, a compact family of spheres, which you don't actually know much about. I mean, in principle, they could intersect like that. But the reason why these spheres are all disjoint is that he showed that if you have two J holomorphic curves intersecting, they always intersect positively. So this would count as +1, and that would count as +1. And that's, of course, impossible because these cohomology, you know, homologically, the intersection is 0. And so the fact that they're J holomorphic means that, in fact, the intersection is 0. So that never happens. And you get families of spheres. You can't have intersections like that. You get another family of spheres. And then, again, these intersections have to be transverse, because if the intersections weren't transverse, they count by more than 1, and homologically the intersection number is 1. So you actually have two families of spheres like that, and using that, you can say, okay, you've got S2 times S2 with this unknown sort of stuff in here. Well, you can use this to just identify your whole manifold. You can, with S2, and using this, you can sort of straighten out omega and show that omega, in fact, has to be the product form. So that's the only thing it could be. So omega, there exists a diffeomorphism, which is the identity near these two things that we assumed, and it pulls back omega to the standard area from the direct sum of these two things. So in fact, this is telling you that the only symplectic form you can have on S2 times S2, which has these two spheres in, is a standard form. And actually, you can extend this to say that if you look at the group of symplectomorphisms of this manifold, which in general is an infinite dimensional group, is actually homotopy equivalent to SO3 times SO3, at least the identity component of it. So it basically, I mean, although it's an infinite dimensional group, because there are always lots of symplectomorphisms because of the Hamiltonian flows and things, homotopically, it's very simple. It's just a product of a rotation in each factor. Now, so that's one of the theorems he proved, and he also proved a similar theorem about CP2. If you take CP2 and you assume you have a curve in here, which is in the class of a line, then their complement, the only thing the complement can be is a ball. And so this is, again, this has a standard complex structure, symplectic structure. So just the usual Taylor form, the Fubini-Studi form on here. So he proved these uniqueness results. And then he also showed what the symplectomorphism group here is just CP2 is homotopy equivalent to the SU3, PSU3, I suppose. So those are some of his results. Now, you can generalize these results. So one of the first things I did was generalize this, where, for example, instead of assuming you have to have two spheres in S2 times S2, you could just have one sphere. If you just assumed you had a single sphere in S2 times S2, you could prove this. Or if you just assumed you had any holomorphic sphere of any degree, you can classify and together with Francois Lalonde, you can classify the symplectic structures on manifold on S2 times S2, on the sort of CP2 blown up at a point, and on S2 bundles over Riemann surfaces. So basically, the Kadara, if you're looking at surfaces with Kadara dimension minus infinity, then as long as you assume that you have some sphere in them, we proved that the forms here have to be the standard forms. So the only forms on this would be a family of, something like lambda omega 0 plus lambda 0, lambda 1, omega 1. So they'd be just products of two area forms. And similarly for CP2 blown up.
Yeah, this is just a translation from the algebraic geometry. How do you think of that as so I think of the blow up as you take away a point and you add a P1. Is that the same as doing
Well, that's something I was next going to talk about. The
okay.
blow up, you have to put a symplectic form on here. And so it's equivalent to embedding a ball.
Okay.
But you still, what does that CP2 CP, for my, the simplest thing is it looks like you've got a -1 curve, you've got a +1 curve. It's a line bundle it's a sort of line bundle like that. Actually, so there are two things I wanted to say. The results of Francois and myself were assuming you had something to start with, at least a sphere. Say a fiber, if you had something with a sphere of self-intersection 0. In fact, any sphere with self-intersection bigger than or equal to 0 would give you this. If you assumed it was minimal, otherwise there's this blowing up thing you have to take care of. If you want to find the surfaces in order then you need to use gauge theory, and I think Tianjun is going to talk about that. So if you feed in some information from Seiberg-Witten theory, that's going to tell you that manifolds which are homotopic, it's going to tell you that there are some curves there if you make some reasonable assumptions about it. So then these are the only structures you can have. So the gauge theory, Tianjun has been working on, extending what you can of the Kadara dimension theory to say symplectic form manifolds. And for that, you need gauge theory, which I wasn't going to tell you about. But that, because the Seiberg-Witten equation to something, then Taub's version of Seiberg-Witten theory tells you have some holomorphic curves in there. As soon as you have a rational holomorphic curve, so these are any surfaces which contain a rational holomorphic curve which are not with non-negative C1, or self-intersection, then you have the standard. You're in the Kadara dimension minus infinity case in the static case.
Yeah. So yes. So there are just topologically only two S2 bundles over S2.
Okay.
The trivial one, which is S2 times S2, and the non-trivial one, which is CP2 blown up at 1.
Yeah, the other thing
we have the two.
Say is if you're an algebraic geometer, you think, of course, there are countably many complex structures on here, right? Because you can think of it as a projectivization of some line bundle of K plus C sitting over CP1, right?
Yeah.
And so, K even topologically gives you that, and K odd topologically gives you that. Now, you don't see the complex. What you see in the symplectic world is you look at symplectic forms which are given a complex surface. You can look at the symplectic forms which tame that complex structure. And so, if you fix so given, you've got an X4 and you've got omega, you can look at all the J, the set of J would be the set of omega tame J. And you can look and see what kind of J's you have, what is this family like? So if you take S2 times S2, which is sort of the easiest case to see, then, if you take it with equal areas, which is what I was doing here, then of course you never see a -2 curve, because that would have negative area, and it couldn't be J holomorphic, because every the taming condition tells you that every J holomorphic curve has got positive symplectic area. You see, J is positive on complex lines. And so any complex curve whose tangent spaces are complex lines would have a positive area. So if you're in the case where the two things have equal area, then the only kind of integrable structure you'll see is a product integral structure, standard. But if you you have a family of lambda omega 0 plus omega 1, where you sort of integrate, you say the integral of omega I on S2, that's always 1. So you normalize. So this lambda could be bigger than or equal to 1. As soon as lambda is bigger than, then you can have a curve in class A1 minus A2, or A1, my numbering is terrible, A0 minus A1, right? So you can have a sort of anti-diagonal, because the form will be positive. And so your J would be stratified. It would have a whole, this space here that I was talking about would be stratified. You'd have a whole bunch of them where the only curves you'd see would be the ones, these ones. And then you'd have some other family where you'd see the diagonal being realized. And that structure, actually, you can see that in the structure of the symplectomorphism group here, because the symplectomorphism group of S2 times S2 with the standard symplectic form is just the product, homotopy equivalent to the product of two SO2 SO3s. But as soon as you add in, you're allowing this anti-diagonal, you actually have a symplectomorphism which rotates around there. You have an element of pi1 in the symplectomorphism group. And that gives you, rationally, it gives you an interesting structure. You have this element of pi1, you have two elements in pi3 coming from the SO3 factors, and they interact to give you something in some kind of Samuelson product, or product that gives you something in pi4, and rationally that's all you see. You just see when lambda is in between 1 and 2. And that was done by Abreu. But if lambda gets bigger than 2, then there's another stratum of J that comes into play, because you can realize, you can realize where S2 minus twice S2, right? A1, A0 minus twice A2. You could one. You can realize that class. In other words, there's another of the Hirzebruch surfaces which you can see is the Hirzebruch structure, which will have a symplectic form of that kind. That means if you look at the homotopy type of the symplectomorphism group, this one goes away, but you get something in pi 8, I believe. And so there's a sort of jumping phenomenon that I worked out with Abreu at one point. And then people have worked out the integral homotopy type. I mean, there's a lot known about these things. I mean, so the point is that you can see some of the complex structure, but you don't see it in the way you expect. It reflected in the fact that you have the symplectomorphism group might have some interesting homotopy theory, something like that. So that's all I really wanted to say about this. I mean, people have been doing more work on it, obviously, but so the second thing I wanted to talk about was blowing up, which is what you'd mentioned about, what happens when you blow up. And here, you see, when you blow up in the complex world, you take a point 0 sitting inside C2, and then you think of the complement C2 minus the origin. It actually fibers over CP1 because for each point which is not in the origin, each point lambda, you have a line through the origin. So you have the space of lines through the origin. And you get, this is the exceptional divisor, and you get this line bundle over here. And blowing up here, you take away a point and you replace it by this exceptional divisor. And that's all you need to do. That's a very robust, well-known process, and you can blow down, and these exceptional divisors are rigid, and if you see one, you can blow it down, etc., etc. Now, in the symplectic world, if you want to do this in the symplectic world, then you need to put a symplectic form on what you get. I mean, locally, you're fine, this is a point, but you need a symplectic form. Now, it turns out that, we've got this divisor, it's a CP1, and it's got a -1 bundle over it. And you look at the symplectic structure near there. The symplectic structure in a little neighborhood, if you look at a deleted neighborhood, you take a neighborhood of the 0 section minus the 0 section, then that is actually symplectomorphic to the region between two balls, say BR minus BR. So it's a spherical shell, just a little like that. And what are these R and R? Well, what would this R be? Well, the thing is, if you have a ball, this is a 3-sphere sitting inside C2 with its standard symplectic structure, then the symplectic structure, when restricted to the ball, becomes degenerate, and it's got one. Every hypersurface in a symplectic manifold actually has a characteristic foliation, as a characteristic null direction, where you can think of this surface as given by some function h equals constant, and then you have the vector field xh, which satisfies the equation that omega dot xh is equal to dh. So it's what's called the symplectic gradient. You take a function, you take the one form, and then you dualize, you get a vector field using the symplectic form instead of the usual Riemannian inner product, but you can use this. And so this is always tangent to the level sets. That's an essential part of symplectic geometry. That's means that every function on a symplectic manifold gives you a vector field, and the flow of that vector field actually preserves a symplectic form. So that means you have lots of symplectomorphisms coming from these functions. But when you have a hypersurface, this xh, if this is true, then if you take omega vxh is dh of v, and if v is tangent to the space h equals constant, then of course dh vanishes on v, because dh is that's the kernel of this thing. So what it means is that if you look at a symplectic form and you restrict it to a hypersurface, there's always a null direction, and that means you get a foliation. And the foliation in S3 is just the usual. It's a family of circles. It's just given by this is just the sum of squares, and you're getting simple harmonic motion, and so that's rotating in each c factor by equal speed. So you get a foliation of this by in fact, if you think of this this is in C2, so it's just take a complex plane through the origin, a complex line through the origin, and that circle is going to get collapsed. And so you can take the S3 and you can collapse it down. So you take S3, 1, and you collapse it down to S3 by the Hopf function. It just collapses these circles. That gives you, until you're collapsing along the null direction, this gets a symplectic form. The form on, omega restricted to that is pulled back from here. And it turns out that the neighborhood of this 0 section is precisely a neighborhood of this sphere in just a spherical shell. You can identify it with a spherical shell. So it means that when you're blowing up a point in a symplectic manifold, what you're really doing, and you're putting a symplectic form on the result, what you're really doing is embedding a ball and removing the interior of the ball and collapsing the boundary. That's what you do to get, so, you know, to blowing up a point in a symplectic manifold is equivalent to embedding a ball B2NR and removing the interior and then collapsing the boundary of the ball via the 2s, well, in fact, to CPN minus 1 via the Hopf function. And that gives you the exceptional divisor, which is a CPN minus 1, gives you a little neighborhood of it being realized in this way. And of course, this works actually in any dimension, but in dimension 4, it's particularly nice because you don't have, you know, these exceptional divisors are -1 curves, exactly what we were hearing about this morning. There are these rigid things you can blow down. Okay, so that's a story about sort of blowing up and blowing down. And of course, there's a lot of work done about this, which I'm going to say a little bit about. But one thing I wanted to say was that it means that if you look at these -1 curves, -1 spheres, from the point of view of Gromov theory of J-homomorphic curves. You know, if you have this is a symplectic submanifold, you can always choose a J, so it's homomorphic. This is a very nice rigid object, right? It's regular. It lives, so the Cauchy-Riemann operator is surjective there. If you start deforming things, it's going to persist. It's very persistent. And you know, the count of these things is 1. You can never have 2 different ones in the same class because of positivity of intersections. If you had 2, you know, this -1 sphere, the class it's in, E dot E, is -1. So, you know, you can never have in the same class, you can never have 2 disjoint things. And yet if they intersected and they were both J-homomorphic, the intersection would have to be +1, bigger than positive. So that's not possible. So that, you know, each class you have a unique one of these things. And if you look at the space of all J, then of course, you know, these exceptional spheres can degenerate, but they can only degenerate into something like a, you know, minus and a -1. They sort of degenerate by further blowing up. And the point is that a -2 curve, that occurs in real codimension 2. So it never happens in a one-dimensional family. Could happen in a 2-dimensional family, but in a 1-dimensional real family, it never happens. So it means that, you know, if you've got 2 families of -1 curves and you connect them by a path, you're doing some kind of homotopy, then you know, they'll just remain. They'll just, along a generic path, this family would remain. So the number of -1 curves would remain. And so that means that, you know, if you have any 4 manifold, M4, a symplectic 4 manifold, it might have some -1 spheres in it, but if it's not rational and ruled, where you could have more complicated classes coming into being, if this is like a torus, or it's a surface of general type or something, and has no spheres, then the number of -1 curves is going to be an invariant and you can just blow them down and get rid of them. So that there's that analog also of the theory of simple minimal models for smooth surfaces, that you can get rid of all the exceptional divisors, except unless you're in the case in the Caldara dimension -infinity case, where it's more complicated. You can't. The more complicated things can happen. But so that's another thing that I proved. So that's another thing that you can always get rid of the exceptional divisors. But then there are a lot of interesting things in symplectic geometry coming to do with embedding balls. So that's what I wanted to talk about. That's another next switch of topics. So does anybody have a question before I go on to that? So the one thing that's Gromov's famous non-squeezing theorem, which for symplectic geometers you know, and if you're not symplectic geometers, you probably don't. So, you know, at the time, people were very interested in the different kinds of geometric structures you could put on manifolds. And in particular, you know, what's the difference between a volume preserving, a volume structure and a symplectic structure? And suppose you have a symplectic manifold and you look at the group of symplectic morphisms of the manifold. So you look at sim mega, and you compare it with the volume preserving morphisms, or perhaps I should say, of omega to the nth, which is the volume form. So every symplectic morphism preserves volume. And then the question was, what is the difference between these groups? And people didn't know, and it was totally conceivable that if you take this group and you take the C0 closure of it, so the unit closure in the uniform topology, so you forget about the smooth structure, but just look at the closure in the uniform topology, it could have equaled that. And Gromov had a theorem which said that, you know, there's a dichotomy. Either the closure, if you look at the C0 closure of this group, it's just this group itself, or it has to be the whole of this. There's no possible intermediate thing it could be. That's, I think, roughly right. That may not be completely right, but I think the simply connected manifolds, that's correct. There may be some other little thing. Anyway, so, you know, there's two alternatives that this could be C0 be closed in the C0 topology. That's a uniform topology. So in other words, that topology doesn't see the derivative in any sense. Or the closure, C0 closure, could be default. And so it was unclear. So in other words, it was unclear what the geometric difference was between a symplectic morphism and a volume preserving diffeomorphism. And what, you know, the way Gromov formulated this was you took a ball, B2NR, and you looked at a symplectic morphism, phi is a symplectic morphism, and you looked at its image. And then you ask, well, what could this image look like? You know, what shapes could it have? What could this ball look like? And he sort of crystallized this into saying, I mean, he's got this ball, and he's got a cylinder here, which is something which looks like a two-dimensional disk, say, of radius r times r2n minus 2. So this is, say, in the first two coordinates. So this is a symplectic splitting. In other words, this is a symplectic manifold with the other coordinates there. So that's a symplectic splitting. And he asked, well, could you take this ball, say, of radius r here, and embed it symplectically into a thin cylinder? So he's thinking a big fat ball and put it in a thin cylinder. And the point is that you can certainly do this preserving volume, because, you know, if n is bigger than, I'm assuming n is at least 2 here, so this is non-zero space, then you can take x1, x2, x3, x4, and then you can take it to lambda x1, lambda x2, 1 over lambda x3, 1 over lambda x4, and that will certainly preserve volume, because you've got the same number of factors multiplied up to 1. But it could shrink. Lambda could be less than 1. It could shrink in the first two ones and expand in the second two ones, and then you'd have a map of the ball into the cylinder. Certainly preserves volume. But the question is, could this be done symplectically? And Gromov showed it couldn't be done symplectically. And the reason is that if you could do it symplectically, if you could put the ball in here, then you can put on a J, so this is which equals the push forward of J0. So that's a standard complex structure there inside the ball. And then he proved that there would have to be some kind of J, there exists a J holomorphic curve through the image of the center of the ball, phi of 0, the image of the center of the ball. So he proved some result about the existence of lots of J holomorphic curves here, basically he compactifies it and then says, well, if you just have the product thing, then you have lots of, you have this thing foliated. Basically, this thing is foliated by disks, which he's compactified to spheres, and this is some perturbation of that thing. So you still have these spheres, they still persist, they don't disappear. So you have this J-holomorphic curve there. You pull that back to here, and that's a a standard J-holomorphic sphere going through the center point. And then he used the fact that, this is a minimal surface. If you use the standard, the usual Riemannian J0, this is a holomorphic curve sitting inside C4. It's actually, or C2, it's actually, or Cn. It's actually holomorphic, and therefore it's a minimal surface in the sense of Riemannian geometry. And therefore its area has to be area at least pi r squared. But this area is seen by the symplectic area here, and this symplectic area here has to be less than or equal to pi r squared, because this is a curve which sits because of the way you've constructed this curve. So that's why he gets r is smaller than bigger using the geometric method, which I'm just sketching for you. But that was an amazing theorem, because the fact that this non-squeezing theorem gave a way of talking about capacities, ways of measuring sizes of sets in symplectic, in subsets of Rn or Euclidean space, for example, and you can show that any diffeomorphism that preserves capacity is actually symplectomorphism or minus symplectomorphism. So this gave you a C0 characterization of what a symplectic diffeomorphism is.
Yeah, because I just want to make just a quick remark. So we're looking here at C0 closeness. Okay, so this is fundamental, because of course for C1, C2 up to C infinity, simp is closed because it's symplectic form. Okay, so it's given on it's given it more on the tangent spaces. So from C1 to up and up, then it's the left hand side is always closed. Now, for C0, it's not obvious at all, because if you take the graph, let's say, of a symplectic diffeomorphism, so you have a symplectic diffeomorphism here. To say that it is C0 closed is to say that if you have a sequence of graphs of symplectic diffeomorphism converging C0 to that graph, it means that they accumulate near that graph, but the limit could be something like this. So it does not converge C1, it just converges C0. And the fact that it is still closed for C0 means that actually that symplectic topology or geometry is based on some kind of capacity. That is, it's very subtle. It's more than volume, but it's less than C1.
The whole theory now that people have developed C0 symplectic topology. So you try and understand how robust symplectic invariants are when you forget about the differentiable structure and just use the topological structure. That's what you're saying. So anyway, this was a very important theory that's led to a lot of developments. So anyway, he also proved it, used these ideas to show that if you have, you're trying to embed two disjoint balls. Suppose we have two balls, B4 R1 and B4 R2, and you try and embed them into some other. This actually works in any dimension. You take the disjoint union of two balls and you try and embed them in some bigger ball of any dimension. Then he showed that you needed pi R1 squared plus pi R2 squared less than or equal to pi r squared. So he gave her, and again, the reason is that here you can compactify this ball here. You can collapse its boundary, so you're really embedding into CP2 and R, and then you're using the fact that if you're given any 2 points here, there's always a line going through 2 points. So you have a J-holomorphic line through there, and you can choose your J so that it's standard on each of these balls. So you have a lot of choice of J. So you take any J which is standard on the image, and here you find a line that goes through. So this has got area of pi r squared. And it goes through the center of these balls. And again, the amount of area you have here is at least pi r1 squared. And here you have pi r2 squared. So if they're disjoint, you have to have this inequality, which is not at all obvious. This is much stronger than the volume of inequality, which should be something about using fourth powers. So this was, so he talked about the embedding of two balls. And then of course, people thought, what about three balls? What about four balls? You know, what can you say? And so, you know, I've looked at this kind of question, and many people here have actually done a lot about it, sort of what can you say about embedding balls. And the easiest thing to do with these balls, you know, the easiest way to think of this, well, one way to think about it is to blow up these balls and think of each of these balls as being an exceptional divisor of some particular size sitting inside, say, CP2. And then you try and well, actually now it's CP2 blown up twice. And so you want to know, you fix the size of this line. So this is where most of our works now work in dimension 4, because we know so much more about the curves. I mean, this result is actually in any dimension, because in any dimension we have a line through 2 points. On the other hand, you know, in dimension 4 we have a conic through 5. So if you do exactly the same argument through 5 points, you get again an obstruction of embedding 5 balls into CP, you know, 4 ball. And so most of the work now is done in dimension 4 from now on, and you compactify, and so you ask yourself what are the symplectic, the cohomology classes of symplectic forms on, in general, CP2 blown up k times. That's if you're trying to embed k balls, you want to know what, so you can fix the size of this. So you fix, okay, my line has got size 1, or whatever size you want it to be, and then how big, what are the constraints on embedding balls there? And you know, for up to k less than or equal to 8 balls, you can actually, I mean, that's the Fano case, as you all know. I mean, everything is very nice, and you can say, you see exceptional classes, you know, the abstractions here, it turns out, so there's a general theorem, perhaps I should explain. There's a theorem which tells you that you know, a disjoint union of balls, say of dimension 4, of sizes Ri, embeds into Q, say of size lambda, if and only if this can symplectically form omega on CP2 blown up n times. In class, well, you want it in class lambda, and so Poincare dual 2 is going to be lambda times the line class plus Ri squared. I suppose the way I've done this, pi Ri squared times the size of the exceptional. Well, perhaps you want to put it. Well, it depends how you do this. But anyway, let's say minus the classes of these exceptional divisors, right? So you can say that, and then the question is, what if you want to know what symplectic forms you can have here? Well, up to, I think if you go up to 8 blowups, then this is sort of the Fano case, and you can use classical methods to say what you get. But if you go beyond any of these, you need Seiberg-Witten theory to tell you what the answer to this is. The answer to this is that by Seiberg-Witten theory, this was proved by Li and Tianjun Li, who's going to come, and Li, who is, I think, is his father, that there's a symplectic form in this class if and only if, well, so let's call this class alpha. alpha. So you need alpha squared positive, which is just a volume condition that the integral of the thing is positive. And then you also need this form alpha to integrate positively over for all the exceptional classes in your blow up, in your manifold here from CP2. So you have a whole, if you blow up lots of times, you have a whole bunch of exceptional classes that could be realized. If you blow up at least 9 times, you have infinitely many. So you have to check that for all these exceptional classes, this form integrates positively on it. And why you need that is because these exceptional classes, you choose a tame J, they will all be represented. So they will be J holomorphic, and therefore the symplectic form is going to be positive on them. So you need these 2 conditions, but it's an if and only if condition, and proving that is not so straightforward. Anyway, but what that means is that we have a precise numerical description of exactly which balls can be embedded into CP2, disjoint movements of balls. And Lalonde, Polterowicz and I think what we did was work it out when we assumed all our balls were the same size. And then it becomes easier, and then you can exactly explain what obstructions are. But in general, the general result needed this result by Lee and Lee, which was about 2000, something like that, or 2000. I'm not exactly sure. Solve the problem of embedding balls. Because it's just this totally numerical condition. And then people started, well, these symplectic embedding problems are very interesting. Perhaps before I go on, though, I can start talking about ellipsoids. Before I mention the word ellipsoids, does anybody have a question? That's the next thing. How do you, instead of embedding balls, let's think about embedding ellipsoids. And there are lots more questions about embedding balls. So Martin has been doing some very interesting work on spaces of embedding. Embed lots of balls and what these spaces look like. Okay, so let's talk about embedding ellipses. And again, I will stick mostly to dimension 4 because in we have many questions and hardly any answers at all. But in dimension 4, we have some rather interesting answers. So and that's what relates to these curves in these unicuspidal curves in CP2. So that's what I want to explain. So what is a symplectic ellipsoid? Well, you've got some quadratic form in 4 variables, x1 to x4, and then you just look at the space of x's such that qxx is less than or equal to 1. And of course, you can change these by this is just a quadratic form. You can change it by symplectic linear transformation, and the linear symplectic group is such that in fact you can always assume that you can look at you can use complex coordinates z1, z2, such that z1 squared over a plus z2 squared over b is less than or equal to 1. So you can always sort of diagonalize, and perhaps you want to pi and that's something like that. Okay. You can always put it in that form. So basically, your ellipsoid is given that this would be the ellipsoid EAB. And so you've got an ellipsoid, you've got one axis there, you've got another axis there. These A's are areas, right? They're the areas of the slices. So then there are many symplectic embedding questions. People were intrigued by Gromov's result about this non-squeezing theorem, and so there are many variants of it. But one thing you can do is look, for example, at the embeddings. Of course, we can look at, take U1A, And we can try and embed it into CP2 of size lambda, say. So that means that the integral of a form over the line is equal to lambda. So we usually use areas as our measurement of sizes. And you can take the infimum, we can fix A and look at the infimum of lambda such that there exists a symplectic embedding. And that we can define to be the function C, the capacity of A. And this would be the capacity function for CP2. So your target is CP2, and you're trying to embed the standard ellipsoid in with that eccentricity A. So A is bigger than or equal to an ellipsoid where, I'm taking the smaller one to be 1 and the bigger one has size A, and I'm trying to embed that in my target, and I'm trying to see how big do I have to dilate the target? What's the minimum dilation I need of the target to do that? And so there was a paper, there are many, many questions of this kind. You can take different. This question, so nobody really, I mean, if you ask this question in higher dimensions, nobody really has an answer. And you can also ask the question if you take one ellipsoid, AAB, and you try and embed it in another ellipsoid, E, lambda C, lambda D or something, and ask when these embeddings exist, and nobody knows. I mean, there's no, in higher dimensions, we have no clue. But in 4 dimensions, we have a complete answer. And the reason we have a complete answer is that I realized that this embedding problem, embedding an ellipsoid into CP2, is actually equivalent to embedding a union of balls in CP2. And the way you can see that is, embedding, so there's a proposition that if A is rational, there exists a weight decomposition, numbers W1 through Wn, such that if E1 P over Q embeds into CP2, if and only if a certain union of balls embeds, this union of this balls of sizes Wi embeds into CP2, and that I haven't actually erased it. That problem is completely solved if and only if there exists that if and only if alpha, which is this class lambda with Poincare dual to L minus the sum of the Wi EI, this with alpha squared is, if alpha is such that alpha squared is positive and alpha integrates positively over all the exceptional divisors. So once you know that embedding balls is embedding an ellipsoid is equivalent to a ball embedding problem, we've completely solved that numerically. We know what the obstructions are.
Is there a relation between the W's and the PQ?
Of course, yes. I was going to explain it. What is it?
Yeah, that was what.
What is it? Well, it's interesting. The way I got this was, and I was trying to embed, say, an ellipsoid E14. And I realized that, I mean, if you think of this, you think of it, this is a toric picture, right? So you used to toric pictures. So I'm thinking of, this is a toric picture. So I'm thinking that, this is sitting inside C2, and on C2, it's got parameters Ri theta I, R1 theta 1, R2 theta 2. And you forget the thetas, you quotient out by the torus action. And so you have, this set of coordinates, R1 theta 1, R2 theta 2, you map to R1 squared, R2 squared. So you're basically, this is what's called the moment map in symplectic geometry. You're quotient out, you're quotienting out. So you're saying that this ellipsoid quotiented out by the two torus action is actually the equivalent to a triangle. It looks like a triangle. So if you're used to toric geometry, you take CP2 and you quotient it out by its T2 action, and then its moment polytope is a triangle like that. And the point here is that each point above here, the inverse image is a torus. The point here, the inverse image is a circle. Here and here, the inverse image is just a point, because that's the origin gone there. And these are the axes. So this is S. This is like you've got an S2 and you quotient out by the circle action, and so it becomes a line. And so you've got these two lines giving you the axes. And this one, and also you can collapse the boundary or not and collapse the line at infinity. So this is what a toric picture would look like. And you know, if you change, instead of taking CP2, you take, which is sort of like it's a compactification of the ball, right? If you take E1A, then you get this would be the inverse image of this disk, and this line will be the inverse image of that disk of area A, and then the rest of it would, you know, you have the rest of it going there. But the point is, once you've gone to a toric picture, you realize, you know, this is that, you know, if you look at the conormals, -1, 0, this one is, well, if I say this is 4, this one is 0, -1. This normal is -1, 4. And then there's a theorem, sorry, this way it's 1, 4. You can see this better perhaps. 1, 0. And then, you know, if the thing was smooth, the determinant, this is 1, 0, 1, 4. The determinant here, this is a non-smooth point because it's got determinant 4. This is a smooth point because the determinant of these normals is 1. And so the point is, you can resolve, this is actually, for those of you who know singularities, I just learned it's a Duval singularity, and it's, you know, you can resolve it, you know, Fulton resolve it somehow, but you can resolve it, you know, you resolve it by blowing up. But when you do symplectic blow-ups, you can, I mean, you can't see that, because you don't put a symplectic form on things. If you blow things up in the complex world, you don't see it. But if you blow things up in a symplectic world, you make your cuts a little bit big. So you blow up like that, and then this becomes a 1, 1. And then this is still singular, so you blow up again. Well, actually, I've done a very bad picture. So if it's, let's do this, is 1, 1, 2, 3, 4. So that's our singular point. So we blow up like that, say. We just out slightly bigger than 1. Then we blow up slightly bigger than 2. Then we blow up slightly bigger than 3. And if you look at this, then this normal is 1, 1. This one, the next. Anyway, you blow up, so the next one looks like that. And then the next one looks like that. So you have a blue normal here, which is 1, 2, and you have a red normal there, which is 1, 3, and then you have the one you had before, which was 1, 4. And if you look at all these things, the determinants of all these determinants is 1, right? I mean, because you've got like 1, 1, 1, 2, and the determinant of that is 1. So these are all smooth. This is now a family, it's a chain of spheres where this is a -1 curve. These are not regular, these are -2 curves. But you can replace your ellipsoid by a chain of spheres. And then the point is that you've got this little ellipsoid in your space and you want to make it bigger. Well, now we use a technique that Francois and I devised to make something bigger. You find a holomorphic curve of C, which goes through this curve and is disjoint from all those, and C squared is bigger than or equal to 0. And then you can deform your symplectic form by basically adding a symplectic form which is concentrated in the normal bundle of C, and then rescaling. So you do what's called symplectic inflation. And the effect of that is you rescale to keep the line of a fixed size. But the effect of that is it makes this one much bigger, and these ones because when you know, if you rescale this curve here is going to hit the line at infinity. So when you inflate, you know, you add something like that, it's going to make the line at infinity bigger. You then divide out by something to keep that line the same size. And the effect is to make this divisor, which is also intersecting, much bigger. This one is going to become much bigger, but all these other ones, which were just little helping things, get smaller. So you can basically ignore them. And so what you get is, in the end, you get a much bigger ellipsoid here that is embedding. So you can start off with a small ellipsoid and make the ellipsoid bigger by this technique. And so that gives you, and that tells you that. So all you need to do to prove this statement is to take your ellipsoid and cut it into balls in the appropriate way. In a way so that this works, so that you have it. Typically, if you look at your picture here, you've got this PQ here, which is, these are both singular points, and you have to cut them up and cut them into balls. And it turns out that when you do that, what you're actually doing is exactly the same as resolving these two singularities. These are two connected singularities. The Duval singularities, you have a way of resolving them by -1 curves. And that way of resolving them by -1 curves involves negative Hirzebruch, negative continued fractions. This way of resolving, if you take an EPQ and you want, E1 P over Q, and you want to say that it's a union of balls, well, the best way to do that is to say, let's take, this is Q and this is P, and then cut it into squares, just by cutting it into squares. So you take these squares of size Q, and then whatever's left over here, you make squares, and then whatever's left over here, you make squares. That's related to the positive continued fraction expansion of these numbers. And there's a relation, these two things, these two singularities at this end, they're related Duval singularities, and there's a relation between the negative continued fractions of this pair and the positive continued fraction of this pair. Anyway, because of the theorem that you've proved that embedding ellipsoids is equivalent to embedding this bunch of balls, which you do by a sort of generalization of the inflation method I was explaining before. And then, this embedding problem is completely solved. And what you're interested in is, the obstructions are coming. Well, this is just a volume obstruction. So that's easily seen. That's just saying that lambda squared has to be bigger than P over Q, right? So that's some pretty obvious volume obstruction up to factors of pi that I'm not going to worry about. And then you have this other obstruction, which is coming from the exceptional divisors in the blow-up. So you need to know, if you take CP2 and you blow it up, what are the relevant exceptional divisors that are going to give you obstructions relevant to this particular family of W's you've got, right? Because there are infinitely many, typically you blow up lots of times, there are infinitely many exceptional divisors, but most of them, they're not going to give you, they're not relevant. The numerics are so far away that they're not going to tell you anything. But here, so the question is, what do you get? So here's the erase. Oh, there it is. Thank you. Okay, so I sort of worked out this how to embed ellipsoids, and then with Felix Schlenk, I worked out what answer we got when we were actually trying to embed ellipsoids in CP2. So we looked at this function, which is this capacity function, which I didn't quite complete. There's my capacity function. Okay, so we're embedding a family, a fixed ellipsoid E1A embedded into CP2 and figuring out how much we have to dilate the target. And that function really was very surprising. So if I quickly try and draw it. And so we have one there. If we look at the volume obstruction, and 9 goes up to 3, this would be like the volume obstruction, right? So we know we have to, our function has to be bigger than that.
The bottom axis is A and the top
This
axis
is A,
is
and this is the,
A.
this is lambda,
Yeah.
right? And then, well, to begin with, which is actually known before, you know, if your ellipsoid is sort of fat, so you're on this thing, you can't do anything. There's nothing funny you can do it to. You just can just embed it. You've got this slightly roundish ellipsoid, and the smallest ball it'll embed in it's exactly the ball of the bigger size, right? You can't embed it. You can't do anything to it. But it was known actually that as soon as you got beyond 2, you didn't continue along that line. That's too much. But in fact, what happens is that it goes all straight here, and we have what's called a full filling at this point, and that you can embed E14 and completely fill out the volume of the ball of the ball there. And then at 5, there's another corner. It goes. So this goes in a line through there, and this goes in this line up to there. This is 5/2. And then it also goes horizontally. And what we found was that we had this family of steps going like this. So there were a whole family, there were interesting obstructions there going to, actually, wait a minute, this is a very bad picture, sorry. This was a very bad picture because this 5/2 goes to 6 1/4. Yeah.
Could you use maybe the yellow,
You don't like red, you can't see red. Okay, what can you see?
The yellow, yeah. You have the yellow just in front of you. Yeah, just in front of you, no, on the blackboard.
Well, I've got orange here.
Okay.
So this is a yellow. Well, well, orange. Can you see that? Is that better?
Yes, it's better. Yes.
It looks like that. It goes up to 6 1/4. And then it goes in steps until you get to the golden ratio, the 4th power. And so there's an infinite sequence of steps here. And then after 8 and 136, there's no obstruction. The obstructions completely disappear. And then there are a bunch of other obstructions here, which we worked out, but you perhaps don't need to, not very interested in. A finite number of other obstructions here. So what you have, this is what you call, this is a staircase because, you know, it's so angular here. And it's called a Fibonacci staircase. Because the numbers here are, I mean, you take the Fibonacci numbers, 1, 2, 3, 5, 8, 13, 20, 134, and so on. You take the ones in the odd places, and then the steps are at with A, you know, on A is on this axis. A is equal to like 13/2. It's a Fibonacci number of the form F 4k plus 5 over F 4k plus 1. And the values are F 4k plus 1 plus 5 over F 4k plus 3. And so we get, you know, these are all, these obstructions all correspond to Fibonacci numbers. And those Fibonacci numbers are, they correspond to exceptional divisors. So each of these corresponds to an exceptional divisor. And it's in class, actually, the degree of it is F 4k plus 3 times L, the Poincare dual of L, minus the weight expansion of this F 4k plus 5 over F 4k plus
Sorry,
1.
I missed something. What is capital F of 4k plus 5? What?
These are Fibonacci numbers. So this is F
4k plus 5 is 4k plus 5 in the
sequence.
Okay, one in the sequence. Okay.
Okay, so this is
Okay.
this is F1, this is F3, this is F5, this is F7. Okay, so you use these Fibonacci numbers, you get a sequence of obstructions, and they give you the obstructions, and they also give you the value. And corresponding to that, you have a sequence of you know, you can take like you have 2L minus E1 through 5, which is one of the ones that give you this, and that's coming from the fact that the conic it passes 2L and it goes through an arbitrary 5 points. So you take a conic through 5 points, blow up the 5 points, and you get an exceptional divisor. But then, you know, all the other ones come in slightly more complicated ways. But yeah, I was going to, I mean, so we've worked out other examples of this. There are other, like for the Hirzebruch, if you take CP2, your target is CP2 blown up ones. And you take this, the line of size 1 and this of size B, so you blow up by size B. So B is somewhere here in between 0 and 1. That's what we call the Hirzebruch surface HB. We completely worked out all the staircases here. And so we have a whole, that corresponding then a whole bunch of exceptional classes, which in the Hirzebruch, the 1 point blow up of CP2. And what is the possible relation of this? Hospital curve?
Sorry, so
Right.
Starting from 9, you know, I mean, this orange curve is exactly the volume curve. Is that forever?
When it's starting from 8 and
Yeah,
136,
exactly. It's always the same.
it's
So it means that when you have very thin, I mean,
well, very similar.
very thin, yeah, then there is no obstruction. Yeah.
That's
And
what,
you have a reason for that?
well, just what happens in symplectic geometry. It's very rigid
Yeah.
in certain situations, and then it becomes more and more flexible, and then all the structure disappears, and there's no obstructions. That's just somehow what you expect. And then this is a beautiful illustration of that fact. I mean, it's like packing stability. You know, you try and pack equal balls into, say, another ball. To begin with, you can only pack 3 balls of particular sizes, 2 balls of particular sizes. But if K is large enough, there's a packing stability. If you have equal balls and enough of them, then you can pack any 4-dimensional surface. In fact, I think it's known more generally in the higher dimensions even. I'm not totally sure what the state of the art is.
What if you have several ellipsoids? Can you pack them inside of?
Well, if you have several ellipsoids, then you know each of them you divide into balls. So if you're embedding several ellipsoids in here, it's again a ball embedding ball. Now, nobody has just yet worked out what you get, what the answer is. I mean, in principle, one could, but I don't know what the answer is.
What do you mean by answer? The characterization?
I mean, well, I mean, you.
Oh, no, this curve. Okay.
But well, you know, what is the actual function you get?
Yeah,
Which would be more complicated because it'd be a function of 2 variables, and there may be regions where it's sort of known. Right, but I don't know. Actually, it would be more than 2 variables. It'd be 3 variables because you have 4 coefficients, and one of them, you know, 4 coefficients of the domain. Here I had 2 coefficients of the domain and fixed one of them. If you have 2 ellipsoids, you have 2 coefficients for each domain, but you can only fix one thing. So it'd be a function of 3 variables. You know, good luck. It would be certainly possible to do. I want to very briefly explain what the relation of this is to unicuspidal curves in time, because it is.
I just have one question, Dusa,
Yeah.
just before. So here the the number A you consider is always rational.
Right.
P over Q.
Well, once you know what it is for rational ones, then you get the rest of it by continuity, right?
Yeah, it's not obvious to me that you get something continuous. Because it all depends on some.
You can rescale. No, you can rescale. You can, you know, you can embed, because embedding, as long as embedding into CP2 is the same as embedding into a ball. So you prove that. So you can be embedded into a ball, and then your ball you can slightly move around. So it's definitely continuous. Yeah, it's not. You're right. It's not obvious. Okay, so. So there are 2 ways of seeing. What's the? Well, one way of seeing this is if you suppose you have.
No.
Via
So for this, you have to find a divisor that avoids your ellipsoid in order to reduce CP2 to a ball.
Yeah,
Then you can do
always
this.
do that by J-holomorphic curve theory. I mean, that was something I proved. I mean, it was proven. It wasn't just assumed. Okay. So what was I trying to say? I was trying to say something about unicuspidal curve. So yeah, so what is a unicuspidal curve? in CP2? Well, it's rational. It's meant to be a rational curve, which is embedded with one cusp. And it's holomorphic, I should say. It's a rational holomorphic. So we're in the complex world. It's a holomorphic curve, which has got one singularity, which is a cusp. And so we're talking about a cusp, which is a PQ cusp. If you have a single cusp, you know, like if you have a 2-3 cusp, you can have a cubic with a 2-3 cusp, then you can resolve this by blowing up, right? You blow up once, blow up. I'm never going to build it, and then you've got this 2-3 cusp. Well, you blow up at this point, and you get an exceptional divisor E, and you get a curve which intersects it twice. I mean, it's a sort of one. It turns into a one. You take a sort of a 1-2 thing. You get rid of the singularity. It still touches it. It's tangent to it, I think.
Yeah, it looks like a parabola.
Yeah, I think
Yeah, it is tangent. Exactly. Yes.
It sort of looks like that.
Yes.
And then if you want to, if you want to get the sort of complete resolution, you blow up this point again, you have E1. So it also, this is tangent, right? So this sort of curves twice, twofold, but then you blow it up again at this point. So this becomes E1, this is E1, E1 minus E2, and this is E2. And then when you blow it up at that point, the two things this is our curve, right? Let's have our curve in orange. Our curve still goes through that point, but transversely. So this is now our proper transform. And then you blow it up again, you get a 2 as a minus, well, it's a 2-fold. This is E1 minus E2 minus E3 now, because you're blowing up at a point on it. This is E2 minus E3. And now we've got, oh, sorry, that doesn't intersect anymore. This is E3. This is E2 minus E3. And here is our curve here. See, now finally, that's a sort of resolved curve, right? And so if our curve originally was in class A, say, then this is in class A minus 2E, 1, because it's tangent to that twice. This is in the class A minus 3E1 minus 2E2. And this one is in class A minus 3E1 minus E2E2. Well, you were blowing up. I think it's minus E2 minus E3. That. So disjoint from that. And it's disjoint from this one. It should be. Substitute. I think somebody who knows tell me that that's correct. I think that's correct. So you blow it up, and so you get this is its resolution. And this now, if you started off with a unicuspidal curve that we're interested in the classification as they're rigid ones, so that the ones which have index 0. So when you blow them up like this, you get a curve. This curve is good. It's a -1 curve. So it's a -1 curve. So it would have index 0. This 2-3 cusp is not good enough because you're starting with a degree thing and this degree 3 thing, and this singularity doesn't sort of have enough oomph to capture all the variation in a degree 3 curve. But the claim is that if you take, there is a classification of curves of this kind, and if you take exactly something like this, which is say a degree 5 curve with a 13/2 cusp, then that exactly, when you blow it up, you precisely get you get an exceptional divisor, which is precisely the exceptional divisor giving you the obstruction at this point, 13/2. It's this one, but it's that's the next one. It is at 13/2. So the claim is that the unicuspidal curves, when you look at their resolution, they're -1 curves, and those are -1 curves are precisely the curves that gives you this give you this obstruction here. And in fact, if you look at the papers classifying these things, I mean, this is classical. There are also curves giving you somehow corresponding to these inner corners as well, which are not, they're cuspidal curves, but they're not rigid. They occur in one complex dimensional families. So you have pencils, the pencil of rational unicuspidal curves decomposed. So anyway, in this paper we were reading, Refkov has a very beautiful construction of these unicuspidal curves, which construct all these curves for you just by using birational transformations, because all -1 curves are birationally equivalent. And Refkov has a sort of twist construction, which constructs them very elegantly from seed curves of degrees, just lines and conics and things, very, very simple things. And so you can, Felix and I worked very hard to show that, in fact, these numerics did describe J-holomorphic curves, because did describe exceptional divisors, because to see that, you not only have to check that the numerics are right, that the intersection is correct and the Chern class is correct, but you have to check that they're birationally equivalent to the standard. You have to look at birational transformations given by Cremona transformation and somehow reduce them to an exceptional divisor. Because you can have fake classes that look as though numerically correct, but they're actually not represented by spheres. So, there's quite a lot of work actually figuring out that these are the right curves. But if you use the complex, you just use this amazing birational transformation that Refkov figured out. I mean, basically, you start off with a nodal, a nodal cubic with its node there. You start off with a curve here, which is properly very much tangent here to this point, like a line which is doubly tangent at that point. And then what you do is you blow up. And so there's your curve. So I'll put my curve in blue. Don't like blue, but never mind, my curve's going to be in blue. So you blow it up there. And then what you do is you blow up here lots of times. Blow it up lots of times. So this is left alone, your curve is left alone, but this becomes a -1 curve. And then, so these are all, these curves are, well, these are all -2 curves when you do it correctly. So what you've done is you've started, so then and this is a -1 curve, so you now blow all those down. So your transformation is that you start off with something like this. You then do a lot of blow-ups at this second nodal point, when you've detached the two nodal points at the second nodal point, you blow up there. And then once you've got to the fact that this thing is now, because it started off by have self-intersection 9, but anyway, you blow it up till it's -1, and then you can blow down this -1 curve and then blow down this chain of spheres until you get something which actually looks like, I mean, this whole thing becomes a new nodal cubic with that thing there. It just sort of, but you've transformed it. So this one, this curve now, of course, this curve is tangent to that. So when you blow this down, it then develops a singularity there, and you blow it down, it develops more of a singularity. So it gets more and more singular when you blow it down. So in the end, you get something which is much more singular. And that's exactly the transformation that takes you from something, I mean, the curves here, down here are just embedded, but the curves here are definitely correspond to singularities, and that's how you construct all these curves of singularities. Oh, this is a beautiful twist method. So that's all I have time to say.
Any theory when there are several cusps?
Well, we haven't, I know in complex geometry, there's definitely questions about how many cusps you can have and things. Yeah, so we just deal with these unicuspidal curves. Yeah, sorry about that. I mean, the other thing.
There'll be a chance of evaluating something special if you take two.
Well, I don't
Ellipsoid.
know, actually. I mean, it might correspond if you were trying to embed several ellipses, you know, different, but yeah, I don't know whether that's true or not. Yeah. I mean, we've been interested in looking at other target manifolds to see what you could say, because I've not seen a classification of unicuspidal curves, say in the one-fold blow-up of CP2. And our methods, we can give a complete family of the possible singularities you might have, but we can realize them sort of symplectically. So we have this symplectic curve, which, you know, it's holomorphic for some non-integrable j, except that j can be integrable near the singular point. So we've got a singular point where everything is holomorphic, and then the rest of it is a sort of generic j. But if you deform that generic j to the complex j, the complex j, of course, is not generic. So we don't know, it could decompose horribly. We don't know. That's sort of where we are with this. Yeah.
Sorry, my voice is not very good. The connection between the unicuspidal curves and the Fibonacci staircase.
Right.
So you found it after you knew the stair.
Right.
You knew already what are the classes giving you the obstruction.
Yeah. I mean, we found out quite a long time ago. I mean, this classification was done actually earlier, but we had no idea.
Yeah, exactly.
Right. I mean, it was just something else.
Once after that, you know that these things corresponds to, say, resolutions of these cuspidal curves. Can we see why these are the obstructions directly from a symplectic point of view?
Yeah, because there's actually, I mean, another way I was explaining the relation of these these two ways of looking at it by looking at the unicuspidal things and looking at the resolution, which sort of immediately gives you a -1 curve. But Kyler Ziegel, who's the person I'm working with, you know, another way you have these curves in CP2 blown up. Well, you can put all the blow up points. You can take this ellipsoid EPQ and put all your blow up points inside the ellipsoid and blow up inside the ellipsoid. And also then you get a curve which and then you somehow stretch the neck around. That's something you can do in symplectic geometry. You've got this hypersurface, you can sort of elongate a normal to that. So you can stretch the neck and tear your target manifold apart. So it's got this, you've got one sort of compact, you've got the line up, you've got the compact piece with the negative end going down, sort of the negative end, which is negative, which end is sort of looks like it's ellipsoid times minus, you know, a copy of R. So you've got this negative end, and then the rest of it sort of goes off to -infinity. And your curve that you have, which has to intersect here because it goes through the line, will become a curve which you know, it sort of does something, and then it goes to the negative end, which is this is at -infinity, and it winds p times round the short orbit on the ellipsoid. You have an ellipsoid, which we now take it as E1 p over q plus, so we slightly deform it, so it's got an irrational rotation number, so that it's got two orbits. It's got a short orbit and a long orbit, and those are the only two periodic orbits. And then you get this curve here, which there's a good theory of J-holomorphic curves in these non-compact manifolds which have this negative end, which is, and it's a curve of finite energy, and you can show what it does is it goes here and it wraps around this orbit, goes around the orbit p times, but it's actually at the same time sort of forming, if you look at a little torus neighborhood of this orbit, it's actually forming a PQ torus knot. And you can, there is kind of constructed an explicit diffeomorphism between the complement of this ellipsoid and the complement of a point. If you take C2 and you remove a point, you can find a diffeomorphism between C2 minus the point and this thing, which precisely will take this curve wrapping to something with a unicuspidal curve. So if you had a unicuspidal curve in CP2, which had a cusp at the origin, and you do rescaling, you will get some curve in the complement of this ellipsoid. And so there's actually a one-to-one correspondence between these curves. I mean, that diffeomorphism destroys the integrable nature of things, but it's a symplectic thing. But so you can see directly that there's a relation between the unicuspidal curve minus the singular point that will precisely go to one of these curves in CP2, which will wrap around with this torus knot end. And that's another way of doing it. And this works in higher dimensions too. I mean, I mean, most of the theory with embeddings works only in 4 dimensions, but this correspondence between unicuspidal curves and these curves in complement, that had nothing to do with finite dimensions. The trouble is that when you look at holomorphic curves in higher dimensions, and especially these ones with sort of negative ends and things, you have to use what are called virtual methods to count them, because you can't choose a J so everything is of the right dimension and you can actually count things. It becomes more complicated. You have to perturb your equation, and then you have to do that in consistent ways so your counts have certain algebraic properties, and none of that is totally well established, unfortunately. So, you know, people want to use more structure there than has actually been proven. So, you know, you can have sort of hypotheses, you know, if you could build this theory where you could count the curves any way you want, then you would get these beautiful results. In dimension 4, what, you know, I've been constantly, you don't really need to use these perturbations so much, and you can, you know, this kind of thing doesn't use any perturbations. We're just using, you know, standard things. We may use a generic J, but we're not perturbing our equation in complicated ways.
Another question?
Yeah.
I have a question about the embedding problem.
Yeah.
So, is there a similar factorization of ellipsoidal embedding side S2 cross S2 also?
Sure. Yeah. You can as long as the target is rational, then you have a characterization. So it could be S2 times S2, and people have worked. There's an analog of this staircase there, which uses Pell and half Pell numbers. I mean, it's very similar. And then you can blow it up 2, 3, I think even 4 times. And people have found analogs of this.
Other questions or comments? So let's thank the speaker.